Hello, my name is Lauren Henderson, and I'm a junior at Calvin University. So a contact binary star, it consists of two stars that are so close that they share a common outer atmosphere. This talk is the third installment in a three-part series. The first talk went over how we use the MESA program to model contact binary evolution, including conservation of angular momentum and mass. The second talk covered how the physics of the systems governed our set of initial conditions. And in this talk, I will present a selection of 5 results from our computations and discuss how we can compare them with statistical observations. So the first result is the relationship between the mass ratio of the two stars Q and their orbital period. Last year, we presented the results of our analysis of the OGLE dataset on the right compared to some rough computational calculations. This summer, we made more realistic conditions that involved one star to instability, which allow us to study the timescales involved in evolution. The plot on the left has period from 0 to 2.5 days and mass ratio from 0 to 1, implying the two stars have the same mass. As you can see, our model results are similar to the observations from OGLE in that mass ratio decreases with longer periods. Knowing timescales of evolution is new with these calculations. This allows us to directly compare our calculated timescales with histograms from the OGLE dataset. The graph on the left shows age on the x-axis ranging from 0 to 12 billion years and period from 0 to 2.5 days on the y-axis. As you can see, the stars stay at low periods for much of their lives before quickly moving to longer periods. This is consistent with the long period tail we observe on the histogram from the OGLE dataset here. If stars don't spend much time with long periods before merging, we should see much fewer long period stars than short period. This result is our modeled HR diagram. An HR diagram plots stellar luminosity versus surface temperature. These gray lines going up diagonally on the plot are the main sequence, which most stars spend most of their time on. Over their lifetimes, stars evolve along these tracks. It has been shown that W-type contact binaries, which are those with shorter periods, are found along the main sequence, while A-types, who have longer periods, are off to the right of the main sequence. Our calculations are consistent with these observational results. As the primary star gains mass from the secondary star, the W-types slowly evolve up the main sequence. Once the primary star ends core hydrogen burning and begins shell burning, stars drift off the main sequence as A-types. They keep gaining mass until they become convective, increase their moment of inertia, and become unstable, which is where we ended our calculations. This drift explains the 2 different positions of W and A-types on an HR diagram. Another result from this summer that tells us about W and A-types is the mass ratio distribution for W-types. Though there is no reason contact binaries wouldn't form with high mass ratios, observations show that most stars have mass ratios less than 0.5. In fact, the first 4 columns on this histogram are where most of the stars are, and you can see that most of them have mass ratios less than 0.5. The plot on the left has age on the x-axis and mass ratio on the y-axis. The calculations show that very quickly after the stars come into contact, within less than 1 billion years, which is on a thermal timescale, stars with high mass ratios drop to lower mass ratios. As you can see, this is consistent with observation. The rapid drop in mass ratio for high Q systems is a result of high mass transfer rates early on, which were actually a surprise to us. Though we didn't predict the drop in Q, the results agree with reality and therefore lead us to believe our computational results are reliable. The final result I will discuss is the relationship between mass transfer rates, which we call m-dot, and fillout factor, which is how deeply in contact the two stars are. Fillout factor ranges from 0 to 1, with 1 being the most in contact they can be before beginning to leak mass through a Lagrange point. The plot on the left is of m-dot versus age. The plot on the right is from our OGLE analysis from last summer and shows fillout factor versus orbital period. As you can see, the stars with high orbital periods here, the A-types, have much higher fillout factors than the W-types over here. As shown on the left plot, the mass transfer rates increase as the star gets older, and as you may recall from a previous slide, period also increases as the stars evolved. So it makes sense that fillout factors should increase as the stars evolve if mass transfer rates are increasing as well. For the secondary star to be able to give enough mass to the primary star to keep up with those high m-dots, they must be in deeper contact. So in summary, our more realistic calculations of contact binary star evolution produce a wide variety of predictions that agree well with observations. So thank you for listening to my presentation, and I look forward to any questions that you guys may have during the live meeting.